Welcome back, everyone. So today we're going to be talking about logarithmic functions. Now, for many of you, this is the first time you're actually dealing with logarithms. So we're going to go slow and introduce you to what exactly is a logarithm, what are our special types of logarithms, and properties of logarithms. So to understand logarithms, you need to understand the basic premise of how we teach mathematics. And the way we teach mathematics is we teach you an operation, and then we show you the reverse of that operation. And from day one, we've been doing this since basically elementary school. We taught you addition, and then we taught you how to undo addition by teaching you subtraction. Then we taught you multiplication, then division. Eventually, you got to foiling. Then we taught you how to undo foiling with factoring. We taught you how to do how to square something, and then we taught you how to undo squaring it by square rooting it. So in the last lecture, we talked about a function called an exponential function. So for example, y equals 2 to the x power. That is an exponential function. And the way it works is you plug in a value of x. So say, for example, I plug in 4 for x, okay? So I say y then equals 2 to the 4th power, which is 16. So when x is 4, y is 16. Now, we want a way of undoing that. We want a function where now we input 16 and we get 4 as the output. So an inverse is something where we plug in 16 and we get 4 for the output. And that's where logarithms come in. Logarithms are basically the inverses of the exponential function. Okay. The inverses of the exponential function. And a way to understand that is by looking at it this way. So we talked about the example y equals 2 to the x. So when x is 4, y is 16. So log, so the inverse function y equals log base 2 of x works like this. We will plug in 16, okay, and say, okay, 2 to what power? So the way of doing, let me illustrate it this way. 2 to what exponent gives me 16? And we saw that the answer was 4. Okay. Now, the general form of a logarithmic equation is log a of x, where this is known as the base of the logarithm. So this is basically how the relationship works. If a to the x equals a number b, remember a and b are numbers, x is just a variable, then log base a of b gives me x. So let's look at some other examples. 3 cubed is 27. Log base 3 of 27 is 3. 5 squared is 25. Log base 5 of 25 is 2. So take home point. Take the base, say 5 to what power gives me 25, okay? And that's how you do the problem. So let's look at another example. Log 2 of 32 equals what? So 2 to what power results in 32? And the answer is 5. Okay. 2 to what power gives me 32? Let's do a couple more examples. Here we go. 10 to what power gives me 100? 10, the base of the logarithm, to what power, which is the answer I'm looking for, equals 100? Answer is 2. Remember, not 10 times, it's 10 times 10, but that gives me 100, but it's 10 squared, or 10 to the power of 2, that gives me 100 as well. A couple more. Okay, let's walk through it again. 2 to the what power to what exponent gives me 1024? 2 to what exponent gives me 1024? And the answer is 10. So this is the way it works. If a to the x equals b, one more time. If a to the x power, x exponent, gives me b, then log base a of b is x. So let's see how that works. A to the x power gives me a number b. A to the x power gives me a number b. So log base a of b, it says a to what power results in b. A to what power results in b? And the answer is x. Now, I know this is a circular way of looking at things, but trust me, with a little practice, it comes. So say, for example, I have a problem like this. Log base 5 of 1. Okay? Now, here's the thing. 5 to what exponent gives me 1? 5 to what exponent gives me 1? Now, if you remember, 5 to the 0 exponent is the 1, it results in 1. Anything to the 0 power is 1. So log base 5 of 1 is 0. Okay? And that is a known property of logarithms. Log of any number to the 1 is 0. Because any base to the 0 power results in 1. Okay. Here's another one. Okay. Let's do the talk. 2 to what exponent gives me 1/2? 2 to what exponent gives me 1/2? So if you remember about our exponent rules, 2 to the negative 1 is the same as 1/2. So that means log base 2 of 1/2 is negative 1. And we can extrapolate. Two to what exponent results in 1/8? 2 to what exponent results in 1/8? Think about it. 2 to the negative 3 is 1/8. So that means 2 to the 1/8, log base 2 of 1/8 is negative 3. I highly recommend that you pause this and do a lot of practice with these problem types, and then come back to understand more properties of logarithms. Here's another one. 16 to what exponent gives me 4? 16 to what exponent gives me 4? So everyone knows that the square root of 16 is 4, but how do I write square root using rational exponents? That's right. 16 to the 1/2 exponent is the same as the square root of 16, which is 4. So that means that log base 16 of 4 is 1/2. So some rules to remember. Log base a of 1 is 0. Another rule, log base a of 1 over a is -1. Okay. So remember, when you raise anything to the negative exponent, you take its reciprocal. So a and 1 over a are reciprocal, so a to the -1 power gives me 1 over a. Or the way you would read it, log base a of 1 over a is -1. And we did an example like that right here. Now, here's a question. Log base 3 of 0. Now, many students will say, okay, well, that's easy, that's 1. Not exactly. Does 3 to the 1 power give me 0? It does not. It does not. Now, that brings the question. 3 to what power gives me 0? So 3 to what power gives me 0? And the answer is none. DNE does not exist. There is no exponent that I could raise 3 to get 0. Yeah, I can raise 3 to the 0 power, but that gives me 1. It doesn't give me 0. But there's no exponent I can raise 3 to, or there's no exponent I can raise any base to get 0. So let's look at our property list. Log base a of 1 is 0. Log base a of 0 does not exist. Log base a of 1 over a is -1. And log base a of a is 1. Well, think about it. A to the 1 power is a. But if the letter a is confusing you, look at it this way: log base 3 of 3. So 3 to what power gives me 3? Well, 1, because 3 to the 1 power is 3. So I got one more property, but I'm going to show it to you through examples. Log base 4 of 4 cubed. Log base 4 of 4 cubed. So 4 to what exponent gives me 4 cubed? So what is the question mark? 4 to what exponent gives me 4 cubed? Well, obviously it's 3. Let's do another one. Log base 5 of 5 to the 7th power. What does it equal? Okay. Think about it. Let's rewrite it. 5 to what exponent gives me 5 to the 7th? Well, obviously it is 7. Last one. Log base 8 of 8 to the 9 d1 equals what? Well, 91. 8 to the 91th power is 8 to the 91th power. So that brings my other property. Log base a of a to the n is n. So these are some fundamental characteristics of logarithms that you should remember. And they come from the very definition of what a log is. Log base a of 1 is 0. Log base a of 0 does not exist. Log base a of 1 over a is negative 1. Log base a of a is 1, because a to the 1 power is 1, a. And log base a of a to the n is n. Right. So let's go back to our discussion of logs. Okay. So let's look at these practice problems. So, A, what is log base 6 of x when x is 1? We talked about an example like this. Log base 6 of 1 is what? 0. B, log base 5 of 1 over 25, 125 equals what? Now, remember, 5 to what power gives me 1 over 125? So since it's a fraction, we know it's a negative exponent. So the question is, what exponent gives me 125? 5 to what exponent gives me 125? Well, 5 to the 1 power is just 5. So 5 to the negative 1 would be 1/5. 5 squared, or to the power of 2, is 25. So 5 to the negative 2 would be 1 over 25. 5 cubed is 5 times 5 times 5, which is 125. So 5 to the negative 3 is 1 over 125, which is negative 3. Okay, last one. Log base 10 of 10,000. So 10 to what power gives me 10,000? Okay. 10 to the 1 is 10. 10 squared is 100. 10 cubed is 1,000. 10 to the 4th power is 10,000. Right. Now, let's talk about logarithms and your calculator. Now, for many people, when you look on your calculator, you'll see a log key, okay? That log key is actually a specific type of log. It is log base 10, okay? And this is known as common log. Common log. Okay, so common log is log base 10. And instead of writing log base 10 over and over again, we just abbreviate it as log. So if you see a logarithm problem without a base associated with it, the understood base is 10. So just like, for example, a variable without a coefficient in front of it is understood to have a coefficient of 1, just like a square root without an index is understood to have an index of 2, we don't write it. So the same way we have log without a base is understood to be common log, which is log base 10. Now, in your logarithm key on your calculator, right above it, is another type of logarithm called ln. Okay, ln. And ln is log base e, which is known as natural log. Now, we've talked about what e is. We said e is an approximate value. It's an irrational number that is approximately 2.718. And we get this as by calculating this expression, 1 plus 1 over n to the nth power. So as n gets larger, as n gets bigger and bigger, goes to infinity, we see that this expression approximately equals 2.718 dot, 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 dot. It's an irrational number. So the decimal neither repeats nor terminates, kind of like pi, okay? So this is a really special number called Euler's number, or the natural base, or Euler's number. And you're going to use this quite a bit in calculating compound interest, calculating radioactive decay, calculating anything that grows exponentially or decays exponentially, like bacterial colonies and stuff like that. So anyhow, the ln number, the ln initial above the log key on your calculator means log base e, and it is known as the natural log. So what I would recommend is to try these different values for common log with your calculator. Put in log 10, common log 10 in your calculator and see what you get. Now remember, log 10 is the same as log base 10 of 10, which remember is 1. So if you plug this into your calculator, you should get 1. Okay, so you hit the log key, hit 10, and then hit enter, and you should get 1. And that's how you use it. Now, if you want to use the natural log key, you're going to have to, for most calculators, you're going to have to press a shift or a second button. And I highly recommend that you guys try these. Try your log key and your natural log key for 1/3, 2.5, and -2. So, question. What would you get if you did this? Log of 0. Now remember, what does it mean? Log base 10 of 0. And we talked about a property that said that we can't do 0. Okay, we can't do 0 because 10 to, there's no exponent that I can raise any number to, any base to get 0. So if you plug this into your calculator, you'd get an error or syntax error. Okay, because remember, this is a does not exist, DNE. Okay, and actually anything less than 0 will still give you that. So for example, if you plug in -2, you'll still get an error, because think about it. Log, common log -2. What is that saying? 10 to what exponent gives me -2? Well, there is nothing I can raise a base to, no exponent that I can raise a base to and get a negative. Okay, I can take the square root of 10. I can make 10, I can raise an exponent to get 1/10. I can raise an exponent to get the square root of 10, but I can't raise an exponent and get -2. So again, you get a DNE, or an error, from your calculator. So you cannot take a log of 0. You cannot take any log, whether it's common log, natural log, or log base anything, of 0 or any number less than 0. Okay, because there is no exponent that you can raise any base to get 0 or a negative number. So you'll get an error if you plug that into your calculator. And we're going to come to this, we're going to come back to this when we're talking about the graphs of logs. Okay, and these are my properties of logarithms. We've talked about the first property, log base a of 1 equals 0, and the second property, and the third property. Now, for the time being, do not worry about this guy right here. Okay, we'll come back and explain that in a sec later. And the fourth property says something pretty important. And I'm going to illustrate it with an example. Log base 4 of, say, 64, and log base 4 of 4 cubed. Okay. Well, log base 4 of 64 is 3. Log base 4 of 4 cubed, based on my property, is 3. Well, what does that mean? That means that log base 4 of 64 equals log base 4 of 4 cubed. And this is pretty significant. What does that mean? That implies that 64 is equal to 4 cubed. Okay. And that's what this property says. If you are taking the log of some variable x and it equals the log of some variable y, that means the variables x and y must be the same. Okay. Now let's come back to the original one, this one right here. Okay. And I'm going to show, again, by an example, what this property says. Let's say, for example, I'm taking 7 to the log base 7 of 49. Okay. 7 to the log base 7 of 49. Remember, an exponent can be any number. Remember, exponents, the exponential function x can be any number. It's the domain is all real numbers. So we can simplify this. Log base 7 of 49, log base 7 of 49 is 2, right? So log base 7 of 49 is 2. So log base 7 of 49 is 2, so we can replace that with 2 and get 7 squared, which is 49. Let's do another one. Log base, oops, wrong, sorry. 9 to the log base 9 of 81. Okay, so log base 9 of 81 is 2. So this is the same as 9 squared, which is 81. One more. 2 to the log base 2 of 8. Well, this is equal to 3. Log base 2 of 8. 2 to the third power gives me 8. So log base 2 of 8 is 3. And 2 cubed, therefore, is 8. So what does that mean? That means if I take, that means a to the log base a of x is just x. They undo one another, okay? These are inverse properties, okay? A to the log base a of x. Write that one more time. A to the log base a of x is just x. Okay. A to the log base a of x is equal to just x. Because what it's saying is taking the exponent and doing the logarithms are inverse properties. They undo one another, okay? So these guys undo, so that's what leaves you with x. Same thing with this. Log base a of a to the x is x. And that was one of our properties of logarithms. So taking the log base a of an exponential cancels that, gives you x. And taking the exponential of a log base a also cancels. That leaves you with x. And these are critical properties. And I know this is a lot of information at one time, but I would say go back, listen to this lecture again, and practice with these properties so that you are familiar with these properties of logarithms, so that you could come back and be able to look into these things without getting so confused, okay? Now, this brings up an interesting situation. This property right here, property number 4, is what allows me to do some basic equations with logs. Okay, some basic equations with logs. So remember, if log base a of x is equal to log base a of y, that means x equals y. This is what we call the one-to-one property, okay? Now, let's see how we're going to use this using it with exponents. So, log, let's look at example A. Log base 3 of x equals log base 3 of 12. They both are log base 3, and we know that they're equal to one another. So if log base 3 of x equals log base 3 of 12, that means x equals 12. You can only cancel those when the logs have the same base, okay? Now, common log of 2x plus 1 equals log of 3x, okay? Now remember, this is a log without a base. That means this is common log, log base 10. So that means both of these logs have the same base, 10. So I can set 2x plus 1 equal to 3x and solve. Okay. All right. So let's have you guys practice this one. Log base 5 of x squared plus 3 equals log base 5 of 12. I would highly recommend that you pause the video, try to do the work by yourself, and then come back for the answer. Now, since both of them are log base 5, that means x squared plus 3 equals 12. Subtract, so how do we solve this? We subtract 3 from both sides. And can take the square root. X equals plus or minus 3. Did everyone get that? Good. Now, let's talk about the graph of logarithmic functions. So this is the exponential function 2 to the x. Okay. The left graph is the exponential function 2 to the x. And we've talked about this graph extensively. We know that it has a turning point and y-intercept at 0, 1. And it has a horizontal asymptote at the x-axis, okay, y equals 0. And this is the graph. Now, exponential graphs are the fastest growing graphs that we have. Since the logarithmic graph the logarithm is an inverse of an exponential, or the way you undo the exponential. And if the exponential is the fastest, guess what the logarithmic graph is? It is the slowest rising graph that we have in mathematics. And if you look at the exponential graph and the logarithmic graph, they are symmetrical across this line, y equals x. This is the line called the identity axis. So the line y equals x has a special name. It's called the identity axis. Okay. And just like we were talking about lines of symmetry with parabolas, the same thing with inverses. A function and its inverse the graphs are symmetrical across the line y equals x, the identity axis. So this is the exponential graph, and this is how the logarithmic graph looks. So let's write some characteristics. Exponential graph, logarithmic graph. Okay. Exponential graph is the fastest growing graph we have in math. This is the slowest. Okay. Now, The exponential has a y-intercept at 0, 1. Well, guess what the logarithmic has? What is the inverse of 0, 1? If you flip the x and y, you get 1, 0. But 1, 0 is not a point on the y-axis. It is a point on the x-axis. So, as exponentials have a y-intercept, logarithms have an x-intercept at 1, 0. Now, exponential graphs have a horizontal asymptote at y equals 0. Okay, and that's because, remember, for example, 2 to the x, there's no exponent that gives me 0. So I can get really close to 0 on the exponential, but I cannot get to 0. So that has a horizontal asymptote. Well, we talked about its inverse. So the inverse of 2 to the x is log base 2 to the x. Okay. Well, remember, what did I say? What can x not be? X can't be 0. So x equals 0 is my asymptote. Well, it is not a horizontal asymptote because this is not a horizontal line. This is a vertical line. So it's not a horizontal asymptote at all. It is a vertical asymptote. And it's at x equals 0. And another name for, just like y equals 0 is the x-axis, another name for the x equals 0 is the y-axis. So if you look at it, these are like polar opposites of one another. They're like a mirror reflection, okay, or bizarro world for those of you who are familiar with comic books. Exponential is the fastest, logarithm is the slowest. Exponential has a y-intercept at 0, 1. Logarithm has an x-intercept at 1, 0. Exponentials have a horizontal asymptote at the x-axis, y equals 0. And logarithms have a vertical asymptote at the y-axis, x equals 0. Okay. And these are properties of logarithms. And these are your characteristics. So remember, the domain of an exponential was all real numbers. And the range of an exponential was from the horizontal asymptote, which was 0 to infinity. But look at logarithms, they're reverse. For a logarithm, the domain is from 0 to infinity because, remember, domain is the collection of x's that x can be, remember? But x can't be 0 and anything smaller than 0. So the domain is 0 to infinity, and the range is all real numbers. So the exponential had a domain of all real numbers and a range from 0 to infinity. Logarithms have a domain from 0 to infinity and a range of all real numbers. And we talked about the x-intercept instead of a y-intercept, and it is has a vertical asymptote as opposed to a horizontal asymptote. So here are the characteristics of a exponential. And one thing I didn't write here was horizontal asymptote. Oh, I did actually, sorry. And here are the polar opposite characteristics of the logarithm graph. Now, for this class, you're not going to have to worry about graphing a logarithmic function. You just need to know the difference between the property difference between an exponential and a logarithmic graph. So the last thing we're going to talk about in this lecture is the natural log e, and we've alluded to it earlier. E is approximately equals to 2.718 ... and it comes from the calculation of 1 plus 1 over n to the nth power, and as n gets very large, it goes to infinity. And I know what you're saying. Well, who the heck would come up with something like that? Trust me, bankers, tax tax collectors came up with it, you know. So if you want to blame somebody, blame the government. Now, E is known as the natural base, and its logarithm is known as the natural log. So, as I told you earlier, log base E, it can be abbreviated ln, natural log. Okay. And it has the same exact properties of every other logarithm. Okay. E to the x, e to the x, and log base E or natural log are inverses of one another. The graph of e to the x, it follows the graph of every other exponential. It has a turning point and y-intercept at 0, 1. It has a horizontal asymptote at the x-axis, y equals 0, and it rises quickly. The logarithm graph, natural log, which is the inverse of the exponential, has a not a horizontal but a vertical asymptote at x equals 0, the y-axis. It does not have a y-intercept, but it has an x-intercept at 1, 0. And you see all the properties of that, all the properties that are true for every other logarithm is also true for natural logs, because it is still a logarithm. It's just log base E. So don't forget that. So natural log is log base E. So 2 special logs that you need to know. A log without a specified base is understood to be log base 10, which is common log. And ln is log base E, which is natural log. And all of the properties that are true for any logarithm is true for common log and natural log as well. So that's the end of this lecture. And when we come back, we're going to be talking about these important properties of logarithms. Namely, how do we evaluate some other log using natural log or common log? So how would I come and evaluate log base 3 in my calculator? So say, for example, I want to evaluate log base 3 of 7. There's no way I can plug that into a standard scientific calculator, because scientific calculators only have 2 types of log keys. They have common log, log base 10, and natural log, log base E. So how do I do log base 3 of 7? In addition, we're going to be talking about this important property of logarithms known as expansion and contraction of logs. And this expansion and contraction of logs, this property that is unique to logs, is important for you to know in order for you to be able to do equations involving logarithms. So until next time, I wish you a good day.